Yeah, hi everyone. My name is Evelina Trutnievite. I'm from the University of Geneva, and I'd like to present the EXPANSE model that we have in the group. So basically, EXPANSE is an electricity system model for Europe. We're actually working also on the whole system model, but for now, what we have is the electricity system. And as you will see later, we have two versions. One is with a high spatial and temporal resolution for a single year. So that is our spatial model. And then we also have a model that models the transition, for example, from today to 2050 at a country level, but then with a focus on uncertainty. And what is special about our model is that we use modeling to generate alternatives to analyze near optimal scenarios that are informed through by history. I'll come back to that. And basically, yeah, it's a model we have developed here in Geneva. So once again, basically here you see the different temporal scales and the spatial scales. So in EXPANSE, I said we have this either model for all 31 European countries where we have a transition from 2020 to 2050, and it's informed through history. So that's why it starts in 1990. Or we have this spatial model. So sometimes we even go, so for now it's 2035 to NUTS 2 level, so very high resolution. NUTS 3 level for Central Europe. And then, I mean, we have in Switzerland, so in Switzerland we even go down to the level of thousands of municipalities. And so the basis for both models is that they are optimization models, technology-rich optimization models or partial equilibrium models. But what is indeed innovative is that we try to bridge the gap between the model and the real-world transition, and we do the uncertainty analysis. That's why all these fish are looking at this strange green fish. So why we do that is that because I mean, from the work that we have done so far is that we see that cost optimization that is used in many models is simply a fiction. So here it's an older study of mine that was done for the UK. So for example, if you take a typical cost optimization model and then you would pretend that you live in the year 1990 and then you model for several decades ahead, you would get a cost optimal scenario, but already using the historical data, meaning there's no parametric, you manage to guess all the future technology features and costs perfectly. And if you compare something like that with the real world, we see there's really quite big difference, in particular, actually, on some of the technologies that we know many models underestimated so far, like wind power and solar photovoltaic. In the case of UK, it's also gas combined cycle turbines, which were actually in the 90s and an innovative and new technology that was coming out at that time. But actually, what is more thought-provoking here for us in the modeling community is that if we look at these dark black lines, which are the cumulative total system costs, and we compare them, we actually see that here in this case of UK, the real-world transition was up to 16% high, more expensive in terms of total system costs as compared to the what was in the cost optimal scenario, which means actually there's a deviation from cost optimality. And then we can also do many Monte Carlo runs to understand, maybe that's the effect of some parameter values. But we see we always get a deviation between 13% to 24%, which means there is really a consistent deviation how real world systems evolve. And that's why that is what in the EXPANSE model then we try to overcome by doing modeling a little bit differently to make the modeled scenarios not cost optimal, but help us get closer to reality. So here now, in terms of spatial EXPANSE model as one example, so basically how it works, we start with input data. I'll speak about that in the moment. Our basic run is still cost optimization as in many models, but then we apply this technique of modeling to generate alternatives to get a large number of scenarios that a little bit more expensive than the cost optimal scenario, but still within the, so to say, acceptable range. And then out of that, we can analyze that. And so in the spatial model, so it's, as I said, the electricity model, we of course need to assume we have different technologies and technology costs. We have electricity demands. It's all spatial data. We know which resources are available and technology availability, and we have both key electricity generation technologies, storage technologies, right? Like batteries and pump storage, so hydropower storage and power to X. And we as well have transmission in the model. Then out of that, we can of course have the regionalized generation portfolios, so also portfolios of installed capacity, as well as system cost and electricity price and regional impacts. And then we also in particular look at equity and vulnerability, and I'll come back to that. So here, for example, we have, in the European model, we can go to, we use a 6-hourly time step for electricity sector modeling. It's an optimized one. We can have a higher one. But basically for Europe as a whole, we can go down to 300 regions. And for Central Europe, we even have, there's a typo here, so we have even more. We can go to NUTS 2 level, which is a higher resolution. And in all of that, we again still simulate many scenarios to understand uncertainty. Excuse me. So basically just a taste of the results. So here it's one of the recent studies where now we have this whole Europe model with almost 300 regions in that. So here we could say, we take 1 year, 2035, and we can think of, how would the electricity mix look like if we basically continue with current generation and storage capacities. So demand will change, so there will still be some changes in the system, but here it's basically a reflection of the current situation just in 2035. And then we can also contrast that with the minimum cost scenario, so with the least cost scenario in here, but it's not written anywhere, but it's a scenario that meets 70% reduction in greenhouse gas emissions from the electricity sector, which would be in line with how electricity sector needs to decarbonize to be for the whole system to be net zero by 2050. And here you see, we at this high resolution, we have all key technologies as well as transmission and so on. So this is the energy part or the electricity part. But further on in our model, we also can quantify impacts. Excuse me. So here, I forgot to say, so here just to show that for this, we can also run this modeling to generate alternative scenarios. So here there's 150 of them. So we assume that we are interested in up to 20% higher total system costs. And here, actually, what you can see is the very large uncertainties that hide in this deviation from cost optimality, especially if we look at wind and solar power. So the cost optimal scenario is here in red. The frozen generation, so basically current situation, is in yellow here. And these MGA scenarios are very, very broad, especially, let's say, for rooftop PV, and it's a little bit interchangeable, whether it's wind or solar. And then for other technologies like natural gas, there's also a range, but then there's also some technologies like geothermal, biogas, woody biomass, that they still actually, the uncertainties are relatively low, even if we allow relatively high deviation from cost optimality. So that was now the energy part, and we still can also here evaluate impact. It's a bottom-up model, meaning it's an indicator-based evaluation. But we have, from that, we can calculate for different scenarios what would be investment and divestment needs. We can calculate locational electricity prices, employment effects, particulate matter emissions, and land use impacts. And actually, in this particular study that I'm showing here, it's still under review. We even aggregate that to overarching indicators. So here what you see that, in the case of all these scenarios that I showed here, to meet 70% target by 2035, which regions in Europe would be benefiting, and it's a score that combines multiple of these impacts. So you see it's more north of Europe and maybe a little bit Spain and so on, well, some parts of Central Europe. But which regions would be more vulnerable because they would be unproportionally affected by higher prices, divestment, and things like that. And you see here there's especially south of Europe that gets negatively affected. So it's an interesting analysis in a sense that it shows that with the transition, we do not necessarily solve these regional inequalities that at the moment we have in Europe, that there's some regions, especially here, that actually get disproportionately negatively affected again. So that's one part. I told you then for the Central Europe, European countries, we can even do it at even higher resolution. So that's, again, I won't go in details here, but it's basically we have both energy parts and then there's all employment and air pollution and things like that. And this is already published, so one can look at it. So that was the spatial model. As I told, we also have this model until 2050 that models the transition. So here, basically, the principle in brief is, again, it's the basis is a optimization model with modeling to generate alternatives. But what is new is that we have 31 models in Europe, so a model for each European country. But we start modeling in the year 1990, so we have 20 years of historical data, and this is fully public data. If you ever need something like that for yourself, feel free to use it. So we use that data to actually estimate how to compare what I showed you before in the case of UK. So to compare how cost optimization in the model, so here it's for Austria, how it would compare with the real world transition historically. And here we find that even in Austria, there was 68% deviation in terms of total system costs in the course of here about 30 years. So it's really a very strong argument why we should not simply use cost optimization. So we basically use data like that to measure, so that's for Belgium, for France, to measure these deviations, and then use that information on deviations to basically also produce scenarios until 2050. In terms of policy instruments and policy questions, so for the policy instruments, it's a bit like, it's quite similar to the other types of models that were described so far. So for now, we work quite a lot with the emissions and energy targets. So it can be, for example, reduction in CO2 emissions, or in the electricity sector, or a certain percentage of renewables and so on. And we can go both at country level or continental level, but we can also have these more specific technology and resource targets. Let's say, is nuclear available, is natural gas available, and so on. We can also add some additional targets if we want on, for example, air pollution or employment or so. We could also add subsidies, feed-in tariffs, and carbon tax. We usually so far have not done it, but it's very easily done. And basically, one of the area we are working with these models is that we want to a little bit more extend into this domain of policy modeling. And in terms of the kinds of policy questions that we worked so far, so of course all of this has lots of information for technology mixes, and in our case, because it's a spatial model, technology locations to achieve the targets. But we also worked quite a lot on the question of equity. So basically how the energy or electricity sector transition, what are its benefits, what are its vulnerabilities, and what does that mean in terms of equity for the different regions around Europe, like I showed you before. So that's for sure a relevant policy question as well on equity. So here I actually won't go into details. This is just this SDG table, but I already spoke about impact, so that's it. think.